Hi guys, I want to welcome you to the class. This is for all of you who just transferred from Mrs. Knight's AP Calculus AB class into my AP Calculus AB classes, because now my classes are huge. I want to welcome you to the class. I want to let you know that you're behind because I've been teaching since we started school, since Success Week or whatever they called that. Because our curriculum is very rigorous. There's a lot going on in our curriculum, and there's a lot that I need to cover in order to make sure you have the information to be successful on your semester exams as well as the AP Calculus exam. So just a little bit about me. I've been teaching math for a long time. I've been teaching calculus for a long time, taught both IB and traditional. Have had 100% pass rates every single year except last year. So we're shooting for that 100% again, because even though we had a COVID situation, I was still not happy with the pass rate. So anyway, I know my stuff. I can help you to be successful, but you got to meet me halfway. What I want you to do is when you go into Canvas, so let me share my iPad screen, because let me actually backtrack. How I teach is I use my iPad, my document camera, sometimes both at the same times. Today I'm just going to be using my iPad, but let me go into there real quick and co-host myself so I can share my iPad screen. And what I'm going to have you do is I need you guys to look over the syllabus that's posted under the modules. So let me join the meeting. And I'm going to take you into Canvas too to show you where it is. There I am. So there's two of me on this recording. And let me share my screen. So it usually takes about 3 seconds for my screen to share, so just bear with me a second. Here we go. All right, and I'm going to go into Canvas, and whether you're in block 1, 3, or 5, I'll just go into block 3. So it looks a little bit different from my iPad screen, but there's this tab called Modules, and if you click on that, let me just reduce these. So they're little. Okay, so these are the modules thus far, and there's a module here called Important Course Documents, and I want you to read the syllabus and the student protocol paper, and there's a document at the end of the syllabus that you need to, actually there's not, I separated it, I forgot, but the student protocol, COVID protocols, what I need you to do, if you look under, I believe it's under assignments. So yeah, this is kind of messy the way it projects here, but you see here it says signed syllabus acknowledgement or signed student protocol. If you go in there and click on the link, you print that out, and you and your parents have to sign it, stating, it just states that you read and you understand the syllabus. And the same holds true for the COVID protocol, okay? I need to have those on file. And what you're going to do is you're just going to take a picture of them and upload them through Canvas. All right, submit them under the assignment. So I'm going to need you guys to do that, and I'll get my roster situated so that way I can see who's new and who's not. I'll have Miss Knight send me her roster too. You're going to have to pardon me. I'm drinking a lot because my throat is sore. Actually homesick. So anyway, that's what you're going to do. Now, I want to go over section 2.1 today for you guys, and this is for you. So I've done this video before. It's posted in the modules. I try to post the Zoom modules, but I really don't like teaching with Zoom because once I record it, it's really hard to find the module, and I can't delete the old one. So it's just like this humongous list of videos that's super annoying, and they take time to process and whatnot. So anyway, way back on 8/25, if I erase this, you can see we started with our syllabus. We started talking about our syllabus. I took attendance, of course, but we started with section 2.1. So you are behind, but you're not that far behind. I don't want you to feel overwhelmed, but I am going to require that you put in some work. You're going to have to catch up, okay? So I'm going to try and get you there. I always post a quote of the day when I'm in school, so I figured I'd post a quote of the day during our lessons together. And just keep in mind that for Zoom, and you're probably already familiar with this, that you need to be on by the tardy bell and you need to stay on until I let you go, okay? So that's not going to change during live lessons. And except for right now, the next few days, I'm under COVID quarantine. It doesn't mean I have COVID. I took the test, but I'm not going to know the results for 3 to 5 days. So I am stuck in quarantine at home. I'm not feeling well, but I don't think I have COVID. And so there's a substitute in the classroom, and I'm just going to post the work on. So for the next few days, you guys are going to be immersing yourselves in watching the videos and asking me any questions that you have, okay? If you need something clarified or if you don't understand something that I do, then I need you to contact me immediately. And I'll be honest, the last few days, because I haven't been feeling well, I check my emails sort of when I get up, and sometimes I answer right away and sometimes I don't because, well, I haven't felt good. And so I'm a little bit slower to respond, but normally I respond right away. So I will try to do that for you guys, including over this weekend, because I want you to be caught up and I want you to feel comfortable in the course. All right, so the objectives were, you're going to find average velocity over an interval of time, and then you're going to estimate instantaneous velocity. And what this is the gateway to what we study in calculus, which is the rate of change, okay, of one quantity with respect to another, okay? And in fact, we look at the rate of change of functions at particular points. Sometimes we look at the rate of change over the entire domain of the given interval for the function. So I use the old book by George Best, which I like way better than the new one, because, by the way, you will have a WebAssign account. However, we can't access the books, and I'm waiting for them to contact me and tell me what's going on. So you can sign up and enroll in WebAssign. You just can't see the book for some reason. So as soon as we get that straightened out, I'll let you know. But in the meantime, if you go into modules, this is super important. I post the book. So if you go in modules, and again, this is just too messy, but you'll see this heading here, best book by chapter. All right. And all of the pages from chapter 2 to 1 to 2, blah, 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 are all listed in here. Okay. Also, let's see what else is in here. Let me go back one. Chapter 2 lessons by date. So I have the book sections link. So here's the book that I'm going to be. So from the old book, I have it scanned by section. So you're going to only be using this book for right now anyway. Calculus is calculus regardless of what book is used, so it's not going to matter. All right. So you have access to all of the pages that I'm projecting here, plus you'll have the video. All right, so let me get started. We get started with the derivative function, okay? And again, we're just studying the rate at which one quantity changes with respect to another here. And George Best does it best. That's the name of the author. He starts out with the notion of average velocity, which is just distance traveled over the time elapsed, okay? Very simple formula. So algebraically, if I gave you, that I traveled 60 miles and I traveled 60 miles in half hour, let's say, well, our average velocity would be 60 over 1/2, right? Or 120 miles per hour. No, 60 over 0.5. Miss Wilson can't do arithmetic, okay? So anyway, it's just distance over the time that elapsed. So maybe I'd put that as 30 minutes or something. All right. So it's easy to plug in some numbers if you're given those numbers into the formula. We're going to make it a little more sophisticated, okay, because that's what we do in higher level math. And we're going to look at it first from a graphical perspective. So in calculus, you'll be looking at things from an analytical or algebraic. You'll be looking at things from a graphical perspective, and you'll look at things from a numerical perspective, which is usually in the form of tables, okay? And I'll show you some of those as well. So in this picture here, in this graph, what I want you to notice is that we're dealing with a distance time graph. Okay, these are all distance time graph. So this is a car that's going on a trip, and it starts out here in its driveway and it travels along to its destination, and it took 2 hours to get to that destination. Okay, and you might be asked to compute the average velocity over the entire trip. Well, the entire trip took 2 hours, so that the interval of time goes from 0 to 2. And all you have to do is connect the endpoints of that interval that you're curious about or that you're asked to find with a line. And this line has a special name. It's called a secant line. It's just a line that joins two endpoints of a curve. Okay? And you find the slope of the line. So what we say is that the average velocity is equal to the slope of the secant line, m sub sec. Okay, this is the secant part here is a subscript. And this point is 0, 0 here, and this point here is 290. So very easily, we know it's the change in y over the change in x, which is 90 minus 0 over 2 minus 0, or 90 halves, which is 45. Okay, so the average velocity for the entire trip was 45 miles per hour because we're in miles per hour. All right, piece of cake, right? You can all do that. I might want to know what the average velocity of this, maybe the first hour of the trip was. So I may ask, what's the average velocity during the first hour of the trip? Well, the first hour goes from 0, 0. This width of the interval represents 1 hour, so to 140. And I would say, well, the average velocity is 40 minus 0 over 1 minus 0, or 40 miles an hour. I could do the second half of the trip, right? Connect them with the secant line. This was 290, I think. And so for the second hour of the trip, I would say that's 90 minus 40 over 2 minus 1, which is 50 miles an hour. So the average velocity, as you can see, is going to change depending on the time interval that you choose, all right? All you do is connect the endpoints of the interval that they're asking for and find the slope of this line, okay? So let me go to a blank page. I'll use this one here. Right now, what you know is that the average velocity is equal to the slope of a secant line, which is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. The change in y over change in x, right? That's just the definition of the slope of any line. We can symbolically write it like this, change in y over the change in x, okay? But I also want you to know there's a few more notations that we're going to use and that you need to become familiar with. All right, so the next notation is f of b minus f of a over b minus a. So let me draw a little graph here. Okay, this is time, this is distance. I don't care what the units are right now, all right? But let's just suppose this point right here is where x is equal to a, and this point here represents where x is equal, or the x coordinate is equal to b, right? So this point, the coordinates of this point would be a comma f of a, and the coordinates of this point would be b comma f of b, right? So if I connected those two endpoints with a secant line, then the slope of my secant line would be the change in y, which is f of b minus f of a, all over the change in x, which is b minus a. And bingo, I get this formula. Okay? No different, just a different way of representing what's going on. A little more sophistication. Let's look at something else here. Let's see. Yeah, where's the graph that I want? Where is it? Here it is. Okay. So now I want you to notice another formula. which is this one right here. All right, so here's where we're going to start getting into some very conceptual stuff. Chapter 2 is very conceptual in itself. It kind of covers almost all of the calculus in a conceptual way, the differential aspect of calculus. In semester 1, you have differential calculus, which deals with derivatives, and in the second semester, you have integral calculus, which deals with the antiderivatives. So anyway, right now we're talking about derivatives, okay? So this new formula is kind of weird, and this is the perfect graph for me to use to explain it, all right? So we have 2 points on this curve. So this is the graph, this right here is the graph of some function f. I don't know what it is, and I don't care what it is, okay? And on this graph, we've got a point A and we've got a point B. Now you notice that below A, the x-coordinate here is A, okay? And down here, the x-coordinate is A plus H. What on earth is that? Well, here's the deal. What I want you to think about is that this graph, so here's the function again. I want you to think that point A is here and point B is like touching it. That's how close they are. And then if we keep blowing this up, then we can sort of see in between the 2 points. Does that make sense? So this picture here, this thing here is the blown up version of this one, okay? So again, we're thinking that our 2 points, again, so here's just some function f, here's my point A, and here's my point B. They're super close together, but when we blow them up, we can kind of make it look like they're far apart. All right, so that's the idea. And so this is the blown up version here. And we might want to, you know, compute the slope of the secant line that connects those 2 endpoints. So here's what we do. We start at point A and we move over some teeny tiny, remember, keep this in mind, this is point A and this is point B. All right, so I'm moving over some teeny tiny little distance, which we call h for horizontal distance. So what is the x coordinate at the next increment? It's the a that we started with plus the h distance that we move horizontally, so we get a plus h. So I hope everybody's okay with that. All right, so when I put this thing together then, or when I think about the coordinates of each one of these points, point A represents coordinates A, comma, f of A. So that's just like the last one I did, not much change there. But point B over here represents the coordinates A plus H, comma, f of A plus H. If I plug an A plus H in, I get f of A plus H out, right? So if I want the slope or the average velocity of this function, it's going to be the change in y. Okay, so the average velocity is the change in y all over the change in x. Well, the change in x will be a plus h minus a. And the a's cancel. So what we're left with is this very special formula, f of a plus h minus f of a all over h, which is known as the difference quotient. Extremely important formula. You need to know this very well, okay? The difference quotient. Oops, I meant to use the eraser there. So let me get rid of this mess. Okay, so this a plus h here, it just means we moved over this really teeny, I mean so tiny that the width of the interval, you know, again, think of point B as being right here or something. All right, and we're looking at this little tiny horizontal distance in between those 2 points. So if I just moved it here, this would be some teeny tiny little amount, okay? That's all it means. So back to my paper then, or I have all these equivalents written down, then what I can say is that this is equal to f of a plus h minus f of a all over h, okay? This is how we find the average velocity of a function or a car, an object, okay, a car, a plane, whatever, over some time interval. This one being super important because this one ties into where we're trying to go, which is the derivative function. All right, so a minute ago, we used this graph here, and we were able to very easily compute the average velocity over the entire interval, which was 0 to 2, over the first hour of the interval, over the second hour of the interval. We could do it over the first quarter hour, half hour, whatever you want to do. Okay, pretty easy. All right, so keeping that in mind now, I'm going to go back to this graph and I'm going to keep using this graph. So for the moment, what I want you to do is I want you to kind of forget about this right here. Okay. And here's the question for which the calculus arises. Suppose I wanted to know what the instantaneous velocity of this function is at exactly when x is equal to a, or t is equal to a, since we're talking about time. All right, if I want to know the velocity at this instant in time, then what I'm drawing here is a tangent line. And we would have to find the slope of that tangent line in order to state what the instantaneous velocity or velocity, and by the way, they mean the same thing, okay? Velocity or instantaneous velocity means velocity at an instant in time. So at this point A, I'm really curious, what was the velocity at this instant? Not over the first hour or second hour or the whole trip, but at the moment when t equaled A. So I have this tangent line here, and we have a tangent line problem because we don't know how to compute the slope of a tangent line because technically speaking, a tangent line only has one point, okay? Namely this point A comma f of A. So what Leibniz and Newton, the inventors of the calculus, did, they said, okay, well, we can find a point really, really close to point A, name it point B, and we could connect them with a secant line and compute the slope. Now, I can look at this, and I know every single one of you can look at this and say, well, this slope may be some approximation of this line, but it's no way close. I mean, this looks like maybe a +1 slope, and this looks like maybe a +1/4 slope or something, right? They're completely different. However, the idea is that if we can get this point B close enough to point A, then maybe the slope of our secant line will approach the slope of the tangent line. So Leibniz and Newton said, well, hey, maybe, if we put point B right here. So in other words, I'm just picking up point B and I'm moving it closer, okay? I'm choosing it to be a point closer to point A. And if I connect point A and point B, well, I can still find the slope of the purple secant line. And would it be a better approximation to the slope of the tangent line? Sure it would. It's going to be better than this slope as an approximation, but I'm still going to be off because the slope of that tangent line is nowhere near the slope of that secant line. So they said, well, hey, let's move B even closer. All right. So we'll move B over here, and we'll connect point A and point B with a little secant line. All right. So this is our new point B. And by the way, think of this. When B was still here, this is my horizontal distance, right? But now when B was moved down the first time when it was purple, you notice this little tiny distance is still called h here, but it's even smaller than it was before, right? We don't know how small it was, but we know it's really small. And then we move B again, okay? Then this little tiny distance h got smaller, okay? And if I move it again to say, I don't know, what color should I use? Light blue. If I move it to maybe here and draw a little secant line, you start to see what's happening. The slope of this little secant line is almost identical to the slope of the tangent line. In fact, they may be identical at this point. But I might need to move a little closer, right? I might need to move that point just a little bit closer, like maybe here, and connect these two. And then what you see is that the slope of the secant line approaches to whatever the slope of the tangent line is. This is called a limiting process. And we're actually not so much moving this point B closer and closer and closer. What we're actually doing is reducing the width of this interval, okay? So we're taking this interval width and we're making it smaller and smaller and smaller, almost to 0, right? At this point here, this would be my A plus H here. This little width is like it's maybe 0.00001 or something. So it's not quite 0, but it's almost 0. And that is super important because when we take this limit or we produce this limiting effect, what we're actually doing is finding the derivative or the instantaneous velocity at the instant that x is equal to a. So with that in mind, we say the following. We say that the instantaneous velocity, which is just equal to velocity, is equal to the slope of a tangent, slope of a tangent line, okay, which is equal to the limit as the width of the interval goes to 0, gets really, really small, I mean so small, okay, of the difference quotient at the point where x is equal to a, okay? So this a in this formula is important because it's at this moment in time. We say this is equal to the derivative of the function at the point where x is equal to a. When you find the slope of a tangent line, you're going to get a number, okay? When you find the derivative of a function at a point, you get a number, 40, 10, 50, whatever, okay? Same thing with the average velocity. You plug some stuff in, you get a number, all right? So you're going to get a value by using the limit of the difference quotient. So all of these things in purple or blue, whatever this color is equivalent here. And everything above it in red is also equivalent for average velocity. Okay? This all means average velocity. And everything down here means instantaneous or just velocity. So back to our picture. At the bottom of this page, which is page 85 from section 2.1, and by the way, in the best book, the section number's up here and then the page number's here. Sometimes the section number's to the right and the page number's to the left, depending. But anyway, this, what I did over here is shown here, okay? And you'll notice that what we need is the average velocity, is the slope of a secant line, which is given by the difference quotient, and the instantaneous velocity is given by the limit of the difference quotient. There's a huge difference. You might be saying, I still don't know what a limit is. It's okay, you will, trust me. Don't worry about that. Pre-calculus is not necessarily a precursor to calculus. The thing is that pre-calculus expands your algebra somewhat. Shows the pre-calculus teacher how good you are in algebra. And if you're really good in algebra, well, then you come to calculus. If you're not, you're going to have a struggle. All right, so some other things about a graph. You notice here there's a graph, a distance time graph, and at different points at t equals 0.75, this is this point right here, there's a tangent line drawn through it. I didn't draw it there, the book author did. At this point here, there's a tangent line through it. So at any point on any graph, I could draw these little tangent lines because this graph essentially has infinitely many points on it, and through every point I can draw a little tangent line, okay? Well, you need to know some things about a graph. The first thing about this graph that I know is that this is distance time, meaning the further this graph goes out, the more distance maybe it's traveled over that time, right? Here, you're sitting in your driveway, okay? Then you take off and you start to drive, you know, and your distance is increasing and your distance is increasing. And then your distance kind of is still increasing, but boom, you hit this spot right here, and if the tangent line is horizontal, it means the slope of the tangent line is 0. So the instantaneous velocity, or the velocity here, is 0 wherever you have a flat spot in a curve, and that means that the object's at rest. So maybe you stopped for lunch, or stopped to use the restroom, or get gas, or whatever, okay, for some period of time. And then when you're done with lunch, you start taking off and you head toward wherever you're going on your trip, okay? The other thing is wherever the tangent line that you draw is the steepest, then that's going to represent when the object is going the fastest, okay? So this positive steep slope in this little area here means the object's going the fastest. So if I were to say in the first hour in this interval here, the object's going the fastest when t is equal to 3/4 of an hour. Here's the other thing. This graph goes from concave up to about here. Then it starts to go concave down. Frown is concave down. And then it starts to go kind of concave up-ish again. So anyway, over this part, I know my object, I'm speeding up. I hit my fastest speed right here. And then my tangent lines start to become going towards 0, right? They're less steep. So what this means is I'm slowing down in this little region here. And then here I'm starting to speed up. Okay, maybe up here I'm going the fastest somewhere in this region. Okay, so those are just things to know about a graph, things to spot. The other thing is that speed does not contain direction. You know, I'll say, how fast are you going? 60, all right? Northeast, no, I just say 60 miles an hour, okay? So speed is just a number, it's a scalar, okay? There's no direction associated with it, but velocity contains direction, all right? So anyway, and it tells you down here, okay, the word velocity is commonly used when direction is taken into account. So we're using the term velocity and speed, which are not the same thing. All right. So I want you to mull those things over. Now the homework for this, let me look on Canvas and see what the homework was because it's closed out. So was this the homework? Yeah. Section 2.1. Problems number 1, 7, and 8. So what your task is going to be after watching this video is you're going to attempt to do problems 1, 7, and 8. And I'm going to open up, I don't know, I'll call it section 2.1 alternate or something. And that'll be dedicated to you guys trying to catch up. All right. And I want you to try those few problems. 1, here's number 7, and here's number 8. Just digest that information, and we'll discuss any questions that you have. Like I said, if you have any questions, I want you to immediately send me an email, all right? And I'll try to get to it as soon as possible. My throat's really killing me right now, so I need to take a break. I'm not going to go on. But digest that information, mull it over, ask me questions, and attempt to do that homework, and you can submit it through Canvas. All right, I hope this helps. Have a great weekend. Bye.